Well, we don't intend this to be a heavy evening, as you can tell from the bar and the snacks that are available. I'm going to say a little bit about, I guess, why we're all here, and then introduce Bob Bindschadler, our speaker of honor this evening. And first of all, it's my pleasure and honor, in fact, to welcome everyone to what's the inaugural Cryospheric Focus Group NI lecture. Many of you may not know exactly where the Cryospheric Focus Group arose or where we're coming from. It's my honor to be here. My name is Sean Marshall, as the immediate past chair of the Snow, Ice and Permafrost Technical Committee, which many of you may be more familiar with. The SIP, or Snow, Ice and Permafrost Technical Committee, is no longer. AGU reorganization and our own sort of directions within the technical committee have taken us to this reorganization as a focus group, which we can think of as a sort of quasi-section within AGU. And the focus groups are meant to spread across several different disciplines within AGU: scientific interests, atmospheric sciences, hydrology, ocean sciences, planetology, global change, paleoclimatology are all reflected within the audience here, I think. As a focus group, you can sort of have three paths, I think. You can grow up and become a section with enough membership. And many of you probably just came from the Richard Alley lecture, where you can see that that's where paleoclimatology is obviously headed, huge membership. Cryosphere is probably a bit small and cozy for that, and will probably be able to remain as we are for many years, I think, which with sort of the new privileges that go with focus group status serve us pretty well. And those include, foremost, I think, being able to host our own sessions, have our own student awards, have representation on AGU council meetings and such. And so the focus group is really meant to serve as a bit of a liaison between members of AGU that are involved in cryospheric sciences and the AGU administration. And it's, again, a great pleasure to introduce to those of you who don't know him, Mark Williams, who I think is here somewhere. Mark, who's taking over as of this year as the new Cryospheric Sciences Focus Group chair. And Mark will be the chair from 2002 to 2004. So one of our initiatives as a focus group that we've discussed in the last two committee meetings, I guess, was to introduce a named lecture to the fall meetings, like many of the other sections and focus groups. And we had a quick discussion amongst the focus group members of in the AGU tradition of who we would name this after, and it was almost unanimous and immediate that it would be John Nye, of course. Because it's hard to think of anyone else that's made the same fundamental contributions to snow and ice sciences that John Nye has made in a period of maybe 10 years in the 50s and 60s. Nye taught us almost everything that we know today about glacier and ice sheet dynamics, stress regimes within glaciers and ice sheets. Incredible body of work. And it wasn't limited to this, actually. Nye's sort of breadth and scale went from microscale up till continental ice sheets, with almost every scale and type of process that's really interesting and important in between, including subglacial hydrology and subglacial sliding, grain scale processes, ice rheology. He's touched on almost anything that you want to delve into as a glaciologist, at least in the glacier and ice sheet world. You can't go far without finding Nye at the heart of everything. I would say that where sort of Nye leaves off and today's lecture begins is a major break in glaciology and snow and glacier and ice sheet work in the past few decades, I think, which is Nye taught us many things, most of what we still know, as I said, about ice sheet dynamics today, but there are a few exceptions to what sort of Nye has taught to us, I think. And if we can think of relativistic physics, the sort of non-Newtonian, then I would say that ice streams are probably non-Nyean. And that they're a very different stress regime indeed. And we've learned, if anything, over the last 20 years, through work that Bob Bindschadler has been heavily involved in and been a leader in, just how important ice streams are and how interesting dynamically they are and how puzzling they are. And I look forward, like I think everyone here tonight, to learning a bit more about ice streams and what we've learned in the past few decades. Bob has come to us with a fantastic sort of glaciological ice sheet and glacier dynamics background. I've just learned today that Bob was Charlie Raymond's first graduate student. in the late 70s at the University of Washington, which is a wonderful pairing, I have to say. Bob was involved early on in surging glacier work in Alaska, evolution of a surge glacier in its quiescent phase. He then went on to ETH in Zurich as a postdoc with Hans Ruffelsberger and Almut Eken. More great work on glacier hydrology, glacier dynamics, fast glacier flow, and then he went immediately from that to NASA, where he's been ever since. And as I said, he's really led the way in the U.S. West Antarctic Ice Sheet program and in unraveling through a combination of field methods and remote sensing and dynamical theory that I would be proud of, really unraveling what's going on in West Antarctica in particular. And without any further ado, I'd like to introduce Bob Bindschadler and leave it to him.
Thank you very much, Sean. I want to start by thanking Sean, not for the invitation, I'll get to that in a moment, but for advocating so effectively for the cryospheric group. All the advances he was describing to you about our stature within AGU did not come automatically, obviously, and it came only because certain people pushed and insisted and advocated that cryospheric science is deserving of such stature and recognition. So in my discussions with people here about how this really came about, Sean Marshall's name comes up again and again. So we really do, as a community, owe Sean a world of thanks and gratitude. Now to my own thanks. I was quite surprised when Sean contacted me and asked me to give this inaugural NI lecture. It was a bit overwhelming just in its concept initially. But the more I thought about it and thought about how John Nye's work influenced me, I really warmed up to the idea and got very enthusiastic about the opportunity to give this inaugural lecture, because certainly where I am and what I know about glaciology is due in no small measure to the work of John Nye. And the way I would characterize John's work, as Sean had also said, he really ran the gamut from all the different scales, and because he introduced the rigors of classical physics to glaciology, I think he accelerated glaciology from its infant state as something that people did almost as a hobby, but accelerated that up to a full-fledged field in geosciences. And I don't think that would have happened anywhere near as fast if John Nye hadn't made the considerable contributions that he did. So I think it is wholly appropriate that this lecture is honoring his contributions. And it really raises John Nye up to the level of some of the other named lecturers here, the Emiliani, the Bowie, the Sverdrup, the Sagan. So it's, again, something very, very good for cryospheric sciences. And I'm sure that over the years we'll have many, many good lectures in this Nye lecture series, and I hope I'm up to giving it a proper start. I assumed that the audience tonight would be primarily people who were not that familiar with ice streams, and so that's how I've gauged the presentation tonight. However, I also knew that within the audience there would be people who knew a lot about ice streams, in fact, whose work I'll be showing time and time again. I've taken liberally from other people's work to put this talk together. And so you'll see a lot of your work, but I think your time here won't be wasted either, because what I'm going to do is sort of tell the story about what we've learned about ice streams and how we came to learn it. Not every little detail, obviously, but try to put it together in that kind of format. So for those of you who have contributed to this work so magnificently over the years, I think it'll be a bit of a nostalgic look, perhaps, and to remind you of how much we have learned and how far we've come over just 2 decades. So with that sort of as the background, we will get started. The justification. I'm going to afford myself a real luxury here, and I'm not going to justify this work other than to say ice streams are really neat. You know, we're geophysicists, and they're just a fascinating subject, and I hope to enthrall you with the mystery that has unfolded as we've continued to work on these ice streams. I'm not going to talk about sea level. I'm not going to talk about collapsing ice sheets. I'm just going to talk about ice streams. Ice streams are neat. If you want to read the details, some of this sort of the connection with the public, in the current Scientific American, Charlie Bentley and I wrote an article that sort of tells that whole story. So avail yourself of that article. I'm not going to be covering that stuff tonight. There's also an AGU publication. If you want to know the technical details, read the scientific papers. Just early last year, AGU published a book called The West Antarctic Ice Sheet, full of wonderful scientific papers by many people in this room, and so I commend that volume to you if you want to read good scientific literature. So I'm going to take you way back to 1973, and for some of you in the room, you weren't even born yet. So this is sort of history book material. Some of us are old enough and have enough gray hair that we actually lived through this time. But I felt the best way to sort of time travel you back to 1973 is to tell you and remind you what was going on in 1973. Remember Watergate? Remember Nixon? That was 1973. He was in the White House, but not for much longer. U.S. military left Vietnam. That was 1973. The Dow Industrial Average stood at 616. Check your portfolio. Things haven't been that bad. The first class stamp cost 8 cents. Gas only cost 39 cents a gallon. These were good days back. These are the good old days, aren't they? MASH was not in syndicated reruns. It was on prime time. For those sports nuts here, the designated hitter rule came into effect. And significantly for me, at least, and I think the topic tonight, I met John Nye. This was when I went to the University of Washington to work with Charlie Raymond. And very fortunately for me, John Nye was there as a visiting scientist. So I got to experience John Nye's approach to glaciology firsthand. And it really did have, as I said, a major influence on me. I'm going to fast forward. This is more for me. I learned some glaciology in those years, and I graduated, and I got hired at NASA. So now we're into 1979. This is an important year to pick up the story of ice streams. But again, I'm going to pull a few headlines, and one that I just could not resist. Okay, we had a change in administration, but this proves the maximum. You can find anything on the web. So I was looking at 1979. And this headline came up, and I knew I had to work it into my talk. This has nothing to do with ice streams. I'll get to ice streams in a moment, but this was just, I mean, ice streams are not the most humorous topic in the world, so I needed a good laugh out of this. So, courtesy of President Jimmy Carter, at his expense. Thank you. Dow Industrials had gone up. Just go through some of these others. First class stamp, now 15 cents. Things getting a little bit worse. Mork and Mindy was popular TV. Oh, yeah, if you like disco, Oogie, 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 remember that big hit? And I met John Nye again. I had spent a year in Switzerland, a wonderful experience there, and John Nye came there, and here I was in the presence of the master. So again, it was nice to sort of bookend my graduate career with interactions with John Nye. But what was going on in glaciology in 1979? Do we remember that? Well, the Ross Ice Shelf Glaciological and Geophysical Survey, the Ross Ice Shelf Project, had just finished, so ice shelves was a major focus during that time. Glacier surges, something I worked on my thesis and continued to work on for a bit, was a major topic, a research thrust. Hans Wertmann had made this statement that basal sliding was the grand unsolved problem in glaciology. I'm not sure we still have it worked out. Glacier response to climate was also another major topic that a lot of us were working on. And again, here, as Sean had pointed out in his introduction, Nye's theories really led the field. And we're going to talk about ice streams. Ice streams were discovered, in a sense. This was 1979 when Keith Rose's paper came out. The data were actually collected in the middle 70s. It was a collaborative project from National Science Foundation and Scott Polar Research Institute and Technical University of Denmark. They flew around, West Antarctica, based at Bird Station, and you can see sort of the flight line grid on this figure. And every so often they saw something in their record that indicated they crossed something that provided a lot of backscatter. And these were crevasses, and sometimes they could see them out the window, and sometimes they couldn't. But they had flown a dense enough pattern that they could connect the dots, and lo and behold, these features that were called ice streams appeared. They really didn't know how fast they went. They were collecting data on the thickness of the ice, but clearly there was something out there. From the ice shelf work, it was known that there was faster ice entering the ice shelf at various locations, and they lined up quite nicely with most of these ice streams. Unfortunately, we weren't quite as creative in naming things in those days, and these ice streams were dubbed A, B, C, D, E. Ice stream B now is called Whelans Ice Stream, and I'll refer to it, and you'll see it referred to in some of the figures, either one way or the other. But these were the ice streams. The interesting thing about ice stream C was that was the one that couldn't be seen visually. There was no surface expression of an ice stream at all there. And so it has always remained an enigma as to, well, why it has shut down. Clearly it has shut down, but the radar was able to detect the crevasses that had been the former active margin of that ice stream. Okay, so the U.S. field research on ice streams sort of followed on rapidly from this, and in the early to mid 1980s, the field research began. I was one of 3 principal investigators, and I remember quite clearly flying in a LC-130 over Ice Stream B at the time with Charlie Bentley, who was another principal investigator, and Ian Whelans. And so this ice stream is now named Whelans Ice Stream in honor of all the work that Ian had done in understanding it. And so we chose to look at 2 different ice streams. One was Ice Stream B, Whelans Ice Stream, because it was active, and they had this chaotic margin on both sides, and it was full of crevasses throughout most of its length, in fact. And then the inactive Ice Stream C. And we felt that by studying these 2 ice streams, we were really looking at the 2 end members of the system, and that would be the best approach to this research effort. And as I said, we flew around and we put a couple camps in place, one in the mouth of the ice stream down here at this, where it says NASA camp down here, and the other one farther upstream at the Upstream B camp. And it's always bothered me that these 2 camps were put in places that were fairly unique on the ice stream, i.e. where a plane could actually land. And so here we were making measurements at these places and assuming that they were typical of the ice stream, when in fact the location itself was atypical of the ice stream. So we had to continually remind ourselves of that. I think with remote sensing we've gotten away from that quite significantly, and with the inclusion of some more adventurous glaciologists like Keith Eckelmeyer, who doesn't mind skiing across one of these chaotic crevassed margins, we went to areas that at least initially we were not inclined to wander. And then we had this mindset, I think, that we carried with us, that we didn't really know much about ice streams, but things in Antarctica are big, and maybe they were just big glaciers. They're just sort of glaciers on steroids, Antarctic scale glaciers. And I think we really did carry that mindset with us when we started to work on these glaciers. And so we assumed that a lot of the work that Nye and others had done on glaciers would also apply to ice streams. Well, we've learned sort of painfully in those first few years that they were not just big glaciers. One way we learned that is to try to apply the usual basal sliding relationship that was being used on glaciers, where the sliding velocity is related to the basal shear stress, this tau b, to some power. And through the work on surging glaciers, we knew that water was important, so we introduced some other factors, this N effective, which is related to the water pressure. And so if you had water pressure, you could increase the sliding. And so we tried to apply those to the ice streams, and they just didn't work. So we really were dealing with something new. I have to pull in some contribution from Terry Hughes, because he'd been working on ice streams long before we actually had set foot on ice streams. And it was something he had pointed out that has turned out really, I think, captures this, this difficulty that we had at the time. He said that if you look at the longitudinal profile of an ice stream that goes from the inland ice all the way from the ice divide, and so this is a longitudinal profile. At the ice divide, you follow the slow-moving inland ice, and it's convex up. It has convex up surface. And then you enter the ice stream, where the ice begins to move faster and faster. It accelerates. But an ice stream has an elevation profile that is concave up. So actually there's an inflection point in between, and the driving stress, which is related primarily to it varies primarily in sync with the variations in the surface slope. You have the highest surface slope at this inflection point right at the head of the ice stream. You have the highest driving stress, so gravity is pushing the hardest on the ice right at the head of the ice stream, and it reduces the gravitational force as you move downstream along the ice stream. So you're pushing it less and less hard. However, the ice is going faster and faster and faster and faster. So that is why these previous relationships simply did not work at all. And in fact, it was Terry Hughes that pointed out we have this inverse relationship. And in fact, that the velocity of the ice stream increases while the driving stress decreases. And that has bothered us for a long time. So we really did have a new glaciological paradigm that I think captured the essence of ice streams at this point. Here we have a picture of Berkeley Cam looking at the till. But before we got to that point, people like Don Blankenship, who were working at the University of Wisconsin at the time, took standard geophysical approach to studying what was underneath the ice without actually getting there, just remote sensing what was under there. And through seismic investigations was able to determine that the material underneath this ice stream was water saturated. It had no shear velocity at all. And so that really surprised us. And then along came the people from Caltech, Berkeley Cam and Hermann Engelhardt, and with their fantastic new tool that they had used on surging glaciers and variegated glacier and Columbia Glacier, this hot water drilling system, set it up on the ice stream and drilled right through the ice stream, and were able to extract an actual sample of the material underneath the ice stream. And that is what Berkeley is looking at here. I've always described it as sort of toothpaste-like in consistency, because I'm not a geologist and I can get away with that kind of sloppy description. But when the experts took this material into the lab and they tested its strength, it really had very little strength at all, and so it deformed very rapidly when it was sheared. So we really had something akin to a perfectly plastic material that with this enormously high power in the relationship, the flow law relationship. So the question really became, okay, if that stuff underneath the ice streams is that weak, why don't ice streams go even faster? So then along came Ian Whelans and had sort of a radical idea and said, we're focusing way too much on the bed. Let's forget the bed. If it's that weak, let's completely forget the bed. And so he looked at an ice stream in a completely different way. And here now we're looking at a transverse section of the ice stream, so it's flowing either into or out of the screen here. And we have this geometry that, again, I think we need to remind ourselves of, that ice streams generally are only a kilometer or so thick, yet they're tens of kilometers wide. So they're really quite thin when looked at in true aspect. In fact, this isn't even close to true aspect. And there is this driving stress on the top surface, and then there's a basal stress at the bed, and then there's on the side, there's a side stress, because there is a side to it. It's only a kilometer, but it does have two sides. And we know from all this crevassing at the margins that there's a lot of shear there at the margins. So you can do a very simple force balance where that driving stress is divided into two partitions. One is the basal stress, and one is the side stress, and you have the geometric coefficient there that accounts for the geometry of the channel. And you can work this out that if the width is about 40 times the thickness, and in fact it's usually more than 40 times the thickness, but I take that as a conservative number here, then you have this relationship. And so what that means is that if the driving stress is equal to just 5% of the shear stress at the sides, then in fact the bed doesn't matter. You can have zero basal stress at the bottom. It doesn't matter what's down there at all. And in fact, if you look at numbers from ice streams, that very often is the case, that you have driving stresses on the order of 10 kilopascals and shear stresses of a couple hundred kilopascals, and so this relationship is satisfied. And okay, the bed doesn't matter. So, but that really wasn't always the case. And the colors here are pretty gaudy. They're much better on the screen. But what this is here is some work that was done about this same time, and we were able to use Landsat imagery of the ice sheets. Some of the ice streams D and E in this case, D is on the right and E is on the left. This is ice stream D as it flows down and enters the Ross Ice Shelf. This is ice stream E as it flows downstream and enters the ice shelf. And what is coded in color here is the velocity, because from sequential Landsat imagery, we were able to look at the motion of individual crevasses. So we could essentially use them as passive markers and get tens of thousands of velocity measurements and look at the detailed pattern of velocity. And this really opened our eyes to the complexity of the flow pattern within these ice streams. But what it also said is that if you have this kind of complexity, and what I've done here is just take this one section here and crop that out, and there's a profile across here. And this curve here that comes up and has a hump and then another hump and a third hump and then back down, that's the velocity or the speed profile across that part of the ice stream. So if the bed doesn't matter, you'd never have that kind of transverse variation in velocity. You would have you'd have a rapid increase in velocity, and it would be straight across and then back down, or very close to that. And that's not what we saw in these two ice streams. And so we knew that in fact the bed did matter, and that's what that says. And so really both the basal stress and the side stress have to be considered. So we sort of ran around that tree a couple times, and I think we settled on the fact that both stresses do in fact matter. So about the same time, okay, now we were already using satellites and satellite sensors to help us solve a number of puzzles about ice streams and about Antarctica in general. And then there was the satellite radar sat, and the Canadians built it. The U.S. launched it, and sort of as a payback for launching it, the Canadians agreed that, okay, U.S., you're really interested in Antarctica. We're going to turn it around. We're going to map Antarctica. And this is an effort that Ken Jezik led, where a ton of data was supplied, and he took these data and mosaicked them into a fantastic map of Antarctica, the first time it's ever been imaged in its entirety at such high resolution. But the other wonderful thing about this mission to map Antarctica was that the time it took to do the full imaging included more than a full cycle of the satellite. So the fact that it was able to repeat some of the same portions of its orbit at the end of the mission that it covered at the beginning, allowed people to do interferometry. And I think everybody knows what wonderful technique interferometry is. And I think actually this work in Antarctica was one of the major reasons that it has such a high profile. Well, this is the map that Ken Jesic's group at Ohio State produced, and it's an amplitude image. But you can take, from interferometry, you can take sections of this and produce these measurements of velocity. So you can see the detailed velocity pattern, and it really is a shame the colors aren't nicer on this, but you still get a sense of these are the ice streams, and we knew the ice streams were there, sort of from the onset areas where the streaming flow, where the chaotic crevassing at the margins really begins, on downstream. We knew about these. This is ice stream A and ice stream B. Ice stream C we don't really see because it's stagnant, it's not moving quickly. And then ice stream D and ice stream E. We recognized all that stuff, but we saw something in this that we had never seen before and never realized was there. And that was this whole portion of the ice sheet upstream of the onsets is full of these tributaries, we call them, that channel the flow of ice into these ice streams. So it's not really, the onset really isn't where the action starts. The action starts far upstream, and these tributaries really were a completely unexpected discovery. But it did allow us to really complete the picture of what an ice stream is. It starts way upstream, hundreds of kilometers upstream from where we had thought, and these tributaries channel and collect the flow. And when you look at where these tributaries lie and superimpose that information on the bedrock topography, these tributaries sit in the deep channels, the subglacial mountainous valleys underneath the ice sheet. And that really isn't, and that's quite significant in terms of what makes these ice streams. So the serendipitous discovery was that we never had bargained on, never expected to have this kind of information that we could do interferometry with, but here it was. And it really had opened our eyes to what was going on upstream of the ice streams. And so these tributaries sit in these deep valleys. And because the valleys are deep, the ice is thicker, and because the ice is thicker, the ice at the base is warmer, and if it's warmer, it deforms more, so it can move faster. And because it's a valley, it collects water. Both of those conditions will help to accelerate the ice. So the tributaries really are the places where the ice streams begin, in a sense, because that's where the flow begins to accelerate. But there's still this interesting question, and Blankenship and Robin Bell and some others have pointed this out, that where this boundary is, this onset, where the tributary stops and the ice stream begins, does correspond to a geologic boundary. Sort of crystalline material, basement material upstream, but sedimentary basin downstream. And that's got the geologists really interested in ice streams. And I have to say that we haven't worked through that completely. There still are some unanswered questions as to whether the onset area certainly is a flow transition. We don't understand the details of that yet because it's making this transition from one type of flow where the basal sliding probably is very much like it is for a mountain glacier. But then you get into the streaming flow where, as I said, the driving stress goes down, yet the velocity increases. So there is something that happens there, and there's this open question of whether the onsets can migrate or whether they're fixed in space by the geology. And that's going to have important ramifications for future modeling. Now, the other thing about tributaries and the fact that we recognized the importance of water at the base for the tributaries' evolution towards an ice stream is that it got us back to thinking about water's importance. And this figure is from some work of Charlie Raymond. And he started to think about water and water production underneath the ice stream. So he was going back to the bed again. He said, let's rethink this. And the primary term in determining how much meltwater is produced is not geothermal heat as much as it is just the heat dissipation due to friction. And that's just the product of these two terms, the basal sliding, the sliding stress again, and the basal sliding velocity. And Charlie pointed out that there really are two extreme cases here, that you have a very well lubricated base, and in that case you have a basal shear stress that's very small, and you're not going to produce very much meltwater. On the other extreme is the sticky bed case, where you don't have a very high velocity, and again, you're not going to produce very much meltwater. So there's a happy middle ground where you actually do produce a maximum of meltwater. It's not out here at the well-lubricated case, it's not back here at the sticky bed case, but it's in between. And Charlie worked out through some equations that it comes out to be that the basal stress is about 25% of the driving stress. And in that case, the velocity for the ice stream is going to be about 40% of the frictionless case, the frictionless case being that of an ice shelf where, again, it's only held at the sides. So it never wants to go as fast as the frictionless case. And then he worked through some more cases of stable and unstable equilibria within this world. But what the other nice thing he did, I think, is sort of bring us back to this formulation of sliding velocity, where he put the basal shear stress back in the numerator where it was, for all the mountain glacier people, and he introduced another term, this tau sub naught, and 1 over tau sub naught can just be thought of as sort of a lubrication efficiency. So he sort of recast this paradigm in a way that was more comfortable to and familiar to a lot of us. And what he also did is remind us that the bed really does matter. Now, sort of about this same time, so what this says is, if the bed matters, then ice streams are not ice shelves. Now, Eric Rigneau made a statement yesterday attributed to Bob Thomas that West Antarctica wants to be an ice shelf. I'd have to take exception to that. I don't think it does want to be an ice shelf. It feels its bed, and I think it does now, and I think it always will. It's not going to lose that. It doesn't want to become an ice shelf. I think that's. I'd have to take issue with Bob on that. And another important ramification of this is that when you think about timescales of things, a lot of work that I just didn't even introduce here was looking at what would go on at the margin of ice streams. And again, Charlie Raymond showed that ice stream margins can move into the ice stream and they can move out away from the ice stream, making the ice stream wider, and there's a delicate heat balance at work there. But that process takes quite a bit of time, and basal conditions can change much faster than that. So if we're worried about and concerned about the response behavior of ice streams, we really need to focus on the basal conditions, I think. And I'll show you some data later that shows you how fast that can happen. At the same time, Slavik Tulicek and was working very hard looking at this till in the lab, doing some tests on it, and I think he's provided the best mechanical description of the behavior of till. We haven't gone away from this characteristic of it being plastic, but Slavik clarified for the community what the state of the till really depended on. It does have this sort of schizophrenic personality. It's either really weak or it's really stiff. And some of the parameters that are most important in determining whether it's really weak or really stiff are how much water in it is in it, what that void ratio is, the dilatancy of the till. The water pressure is still important. We can't get away from that. But most of the ice streams, the water pressure is close to flotation. They're almost afloat. In some places they are afloat, but still doesn't want to be an ice shelf. But the basal heat balance is also really important, because that determines whether the amount of water in the till is increasing or decreasing. And there was this focus on basal heat balance that I think leads to this next slide. And it was the subject of most of what Christina Halba presented yesterday, talking about areas in West Antarctica that get too thin and stick. And it's the same story that she was presenting, I'm presenting here, that slice an ice stream, And you look at this profile through it, so you have ice sitting on top of till, and what's shown in, what color? That's just black, isn't it? This curve is simply the temperature profile, the vertical temperature profile. So it's cold at the surface, cold atmosphere, and it gets warmer and warmer with depth, and then you get at the pressure melting point at the base of the ice stream, and then it continues to get warmer because of geothermal heat coming up. And so the heat balance at the base of the ice stream really is just how rapidly heat is being supplied from beneath, how rapidly that heat can conduct up through the ice, and there's also this sort of wild card term of water flowing in from outside of that area, from upstream, flowing along the interface between the ice and the till. And that's sort of the whole picture of subglacial heat balance in a nutshell. So let's look at that. Let's start from a particular point on what I'm going to describe as the cycle here, where the rate at which heat is being conducted up through the ice is insufficient to get rid of all the geothermally supplied heat. So if that's the case, you're going to be melting ice into water, and you're going to have a well-lubricated bed, and you're going to have the ice accelerate. You're going to have streaming flow. But if you're accelerating and the ice stream is activating here, the ice is going to be getting thinner as that happens. And as it gets thinner, this is happening fast enough that other thermal processes can't take place. It can't adjust quickly enough, and by thinning the ice, you still have the cold atmosphere, so you still have the same temperature difference between the top and the bottom, but you've increased the thermal gradient there at the base. So you increase that gradient, it can remove heat more quickly, and so it can now accommodate all that heat that's coming up through the till, and in fact there's a deficit, and now you're going to freeze water and turn it into ice. And that's just the condition that flips the till from this weak state to this stiff state. So the bed's not as well lubricated anymore, and so it decelerates, it stagnates, but after it stagnates, it sits there and it thickens due to snowfall. And you have this cycle of ice stream behavior that at least is one possible explanation for why ice streams stop, like we know ice stream C stopped, and it also indicates that ice streams can reactivate through this process. Well, the people at Caltech were persistent in always going to the ice streams every season they could and drilling holes, and they get better and better at providing fabulous information to us. In this case, these were a few frames from millions of frames of video that were collected. In this case on ice stream C, where they drilled through the ice stream about a kilometer thick. And on the left there you see a downhole shot. So you're looking right down through one of these ice streams. And through most of the thickness, more than a kilometer of the thickness, they would go through regions of clean ice. Sometimes the ice had bubbles, like the one photograph there, and sometimes it didn't have bubbles. It was clear ice and not too much to look at. So after waiting for a kilometer of that kind of video, you get to a far more interesting story when you get near the bed. Now remember, this is ice stream C. This is the ice stream that we know stagnated. And so let's look just at that last 11 meters at the base, and there was an open pocket of water underneath. That's indicated by that blue field. And as we enter this last interesting bit, there's clean ice. You know, we've had more than a kilometer of clean ice, really getting boring. And so interesting stuff happens. We start to see that there's some inglacial debris has been frozen into the ice near the base. Not too much of it, just 1 or 2% by volume, but a little bit. And sometimes it's layered. And Slavik Tulicek had a really nice poster earlier this afternoon about this. Then get down, that was about 10 meters worth, and you get down to the last meter and a half, and you really start to pick up a whole lot of debris. And it really starts to get dirty down there, in some cases up to 50% by volume. And then right at the base, now this is, again, a downhole shot, you're looking right at the base of the ice stream into the water void underneath, there was about 10 centimeters of very clean ice. Okay? So Richard Alley has come along at the last waste meeting in September and attempted to explain this, that, okay, the clean ice, that's when you have this active ice stream, it's sort of ripping along, there's melting going on at the base, it's real happy and it's just galloping. But then you start to get some freezing at the base. But what you're probably freezing is this water that is not local water, but it's coming from upstream. So it's flowing along this interface between the till and the ice. And so you're freezing more water, but every so often it just picks up a little pebble from the till. So you'd expect to have far more ice than debris in that portion. But once you get rid of that water, and you're still in a freezing situation, the only thing you've got left to freeze is the water that's in the till. So when you do that, you really incorporate a lot of that till material at the same time. So that's why that last meter or meter and a half is so dirty, because you're freezing the water that's in the till, and then it's believed that this last 10 centimeters is just a result of it sitting on top of a cavity where there is some extra, some reservoir water, and that freezes on again without any till. So that's the picture that I put forth as, I think, the general consensus of what's driving this cyclic behavior of ice streams. But it begs the question of what's the right time scale for this. And this gets a little bit scary because, okay, you can start at the long end and you can say, well, you know, a millennium. There are variations in ice stream flow that take us many hundreds of years out. In this case, we're looking at, this is an active ice stream right now, ice stream D. This is the inactive stagnant ice stream C. But there was an interesting feature just on the upstream side of Sipal Dome, this scar feature. Charlie Raymond and Twit Conway and Ted Scambos and Nadine Narrison went there, and they found that the scar feature was just like the margins of ice stream C. That is, there are buried crevasses, and by noting how much snow has accumulated over top of these buried crevasses and knowing the accumulation rate, you can date how long ago that was an active margin and for how long it's been inactive. And in this particular case, this Sipal ice stream, they called it, had become inactive 450 years ago. And there are other similar investigations elsewhere around West Antarctica where these ice streams are, and there are other relict ice streams. So we know that there have been previously active ice streams in different locations on this time scale of close to a millennium. And then also that this is some of the streak lines that Tina Hobel was discussing yesterday. This particular set was perhaps I think the first one. Gino Casasa noted this bulge in these streak lines. This gray arrow indicates the current velocity direction, and clearly the misalignment indicates that there have been some major changes in flow in this area, and through some work that Mark Fonestock and others did, that event was timed at about 550 years ago. So we know that there have been changes on that kind of time scale, on millennium. And we can also bring that down to the century time scale. As I said, ice stream C was stagnated. I neglected to say that, again, through that same process of noting how deeply buried the formerly active margin is, where the shear crevasses were formed from an active ice stream. Ice stream C was dated as shutting down about 150 years ago. And then Steve Price noted that if you look at the upstream area of ice stream C, this is the direction that ice stream C used to go, and there's lots of these flow lines, the streak lines that indicate its direction. I've amplified a couple here with these black lines that show the flow boundaries. On the upper part of this figure is ice stream B, and flowing much faster in this direction. But the velocities that Ian Jochen was able to produce from the interferometry show that when you superimpose these two, that the velocity of the ice that used to be traveling down ice stream C has now turned and sort of spills into the head and the side of ice stream B. So there's a significant redirection of flow there on the time scale that is certainly shorter than the 150 years that ago that ice stream C shut down. Well, let's keep going. Let's keep going to the decadal and annual time scale. Do we see changes on that time scale? And in fact, we do. Here I'm showing Whelans Ice Stream, and these aren't velocity vectors. These are the difference in two velocity vectors. So the ice stream is flowing this way, and the arrows are the difference between the velocity 1 to 2 decades ago and the velocity more recently, just a few years ago. And all of the arrows point upstream because it's going slower now than it used to on the decadal time scale. And it's going slower not just in the mouth of the ice stream where a discovery that had been made earlier, but all the way up to as far upstream as we have measurements. All these velocity differences point upstream. And the magnitude of the deceleration that we see pervasive across this entire ice stream is on the order of 1 to 2% per year. So it's, you don't have to go over very many years before you have a really significant change in flow of this ice stream. Well, hang on, because we're going to go down to daily and minute time scale. And some of the work we've been able to produce from measurements we've made in the mouth of Whelans Ice Stream. So this is just that one area right where ice stream B, Whelans Ice Stream, empties into Ross Ice Shelf, has shown velocity variations on incredibly short time scale. So what we're looking at here in the upper part is the position plotted every 5 minutes. And you can't really see those dots. What you see are these larger dots that are the hourly positions from that. And so what we see is that over the time scale of just a few minutes, it lurches forward, and then it sits there for hours. And then it lurches forward again, and it sits there for hours. And so it's this stick-slip motion that we've seen on the ice plane of Whelans Ice Stream. This, for scale, is a meter. So it moves the better part of a meter in a day. And it does 2 of these motion events, these stick-slip events, every day. Down here, the spiky curve here is the speed. So when it's lurching forward, that's a spike. And then another spike. This is an artifact, and then another spike and another spike. And the dashed curve then is the tide. And in fact, they correlate extremely well. And at least in the area where we have studied this, we see 2 of these motion events a day. One is just at the latter part of high tide, don't know why, and the other one is on the middle of the falling tide. So twice a day. And when it's moving fast, you know, these segments here where it just zips forward, it does that in about 20 minutes or so. And when it's the average speed that it maintains when it's moving through one of these motion events is, I say here, about 22 kilometers a year, which is the frictionless limit. So for twice a day, it's sort of like the watch that's broken is right twice a day, 2 times a day. It's an ice shelf twice a day. You know, it completely loses any friction it has on its bed, and it just zips forward and it just sits there. So twice a day it thinks it's an ice shelf. And we also, and Whelans is not the only place this kind of tidal response is seen. This is the only place that's as dramatic as this. But even on the stagnant ice stream C, we can tell that the ice stream hears the tide and knows that the tide is going through its oscillation. And then on ice stream D, which is another active ice stream, it too has a tidally forced variation in its velocity. Plus and minus 50%. It's not quite as radical as Whelans Ice Stream, but it's there. So this system is a pretty wild system. So what I say here, this is a huge playground for a physicist, and sort of getting back to the fact that Nye is foremost a physicist, I would say. And there's a lot of room to play in this playground. I indicate on the left here the spatial domain goes anywhere from the length scale of an ice stream, which is a few hundred kilometers, down to the thickness of this water film that moves along the interface between the ice and the till. And that's 1 millimeter and less. So you've got a huge range in spatial domain. You've got 9 orders of magnitude to play with. Then on the temporal domain, it's almost as robust and as large. You have on the long side the retreat. We know the West Antarctic ice sheet retreated about 10,000 years ago. So you go to this time scale of thousands of years. There are large variations in this whole ice stream driven system. The deceleration and stagnation that occurs probably on time scales of a century or so. But you have to take that time scale all the way down to the tidal cycle, because we see the system respond radically to the tidal forcing, just a matter of minutes and hours. So on the temporal scale, we've got 7 orders of magnitude. So this really is a huge parameter space, which might be, I think had we realized it was that big, we might not have ever gotten started. But we kind of stumbled onto this, and we're into it now. And I think the real take-home message is twofold. One is, this is just a fascinating system. And it's been sort of like peeling the layers of an onion. I mean, it has been a marvelous voyage of discovery, and we thought it was just, glaciers on steroids. It's anything but. It's sort of a very unique feature on planet Earth. And the other take-home message is that we've made remarkable progress. I mean, for having stumbled onto this topic some 20 years ago and thinking in a very simplistic way about what we were about to study, we have made enormous progress in unraveling the incredible enigma that these ice streams present. And I think as testimony to that, you can take all the modeling of ice sheets from papers probably dated before 1990 and throw it out. I mean, we didn't even know what the right physics was. But we're now getting to the point where we understand a lot of the physical processes within this system, fascinating as it is. And because we're getting a firmer handle on the physics, now these models really are turning out to be very useful. And I call them here flexible workhorses, because I think more and more of the work is going to be done now parameterizing the physics that we now understand and being able to incorporate that in the models to be able to sort out what's really going on in the spatial and temporal domain. As I said, it's huge, and we don't really know what the interconnections are, and I think it's going to be the role of models to allow sort of one process that's working on time scales of hours and minutes to operate at the same time another process is working that has a sort of a natural time scale of centuries. I think models are going to be the way we do that. But we do need more observations. We just can't sort of start buying computers and not going to the field anymore. It's been, again, astounding how much information has come from the drilling that has been undertaken by one group. It's only been the Caltech group that has drilled, but every hole that they drill tells us more and more about the system. But when you add it all up, there really haven't been very many holes drilled. I say here, nature may have been kind. And what I mean there is that I showed you what radical behavior we see forced by the tide in the mouth of Whelans Ice Stream. The till goes from a very weak state to a very stiff state in a matter of minutes. We couldn't have asked for a better experiment to help us understand the behavior of till. When we grabbed the till and went to the lab, that's sort of the experiment that we ran. Well, nature is running that experiment every day for us. We have to go there and take advantage of that. And if the behavior of the till that results from understanding what's going on does scale up in the temporal domain, is temporally invariant, then I think we've got the physics of the till that is central to the whole understanding of the response of the ice streams, which is central to the response of the ice sheet, right there in our hands. So nature's doing the experiments for us, and we couldn't have asked for a kinder hand dealt by nature. And then, of course, once we learn, it's not just about West Antarctica. I didn't go through the whole marine ice sheet story. What makes West Antarctica fairly unique today, but there were previous ice sheets that were very similar to West Antarctica, that occupied deep marine basins like the Baltic Sea and the Hudson's Bay. And so what we learned about the ice streams today, I think, are going to help make understanding what happened to those ice streams and the Heinrich events and all the climatic and paleoclimatic information that Richard Alley was talking about. I think all of this information will be directly applicable to that, as of course it will be to the future, which is what a lot of the policymakers and decision makers here need to know. So I think we've come an extraordinarily long way in 2 decades. I hope those of you who have participated in this, and there have been just a long list of people who have done magnificent work in this area, feel good about how much we have learned. I think we have come most of the way to getting to this ultimate goal of being able to predict the future of the West Antarctic ice sheet. And I hope those of you who came not knowing anything about ice streams are also equally feel equally good about learning about something that's really fascinating on this planet Earth. And certainly because we have not solved all the problems yet, good physicists are still needed, and there's still a bit of work to do. But it's been a fabulous ride, and I hope you get a sense of that from what I've presented, and thank you for your attention.